Okay, so with our UV catastrophe, what classical physicists thought? Classical physicists thought, let's say that we had sodium absorb a lot of light energy. Let's just say that we had sodium absorb some amount of energy. And sodium, according to a classical physicist would say, this electron here that's on the outermost ring. So if I look at my sodium, I see that, I'm trying not to move this, guys. I see that this electron here is the only one that's on the outermost ring. What this means is that electron is going to want to start to vibrate. It's going to vibrate and shake in a way that it's going to want to become removed from, it's going to want to try to remove itself from the atom. Now, we know that electrons can definitely leave atoms. That's how we get static electricity, because there's a transfer of electrons. So I think to a classical physicist, it makes sense that electrons are able to leave. With this, classical physicists would say that since electrons can oscillate at different frequencies, which means that they can emit light in different wavelengths. So that's the reason that we can see different amounts of light, is because electrons can travel at different frequencies, they can move at different frequencies, so then that means that we can see different colors of light, and that's true. Classical physicists would say then that because of this, we're always going to see a continuous spectrum, which just means that we're always going to see a spectrum where it's just a full rainbow all the time. If that were true, then everything that we would see, we would never see a dominant color. That just means that everything that we look at, we would just always be seeing a rainbow for everything. Like your skin would be a spectrum of color. Your clothes would always be Roy G. Biv. Everybody would be wearing rainbows. Everything would be a rainbow all the time. Classical physicists also said that radiation that's emitted from a black body predicts the intensity, and that intensity is inversely related to wavelength. So if you will look for me on slide number 5, there is a graph, and I think that this will help us maybe visualize this a little bit, because this is the difference between classical theory and between modern theory. And this is where it all started, okay? A classical physicist thought that radiation that was emitted from a black body, the wavelength is inversely related or inversely proportional to intensity. So what do I mean by that? It means that as wavelength gets smaller, your intensity gets greater, or vice versa. As your intensity decreases, your wavelength will increase, or your wavelength will get longer, okay? Let's look at this graph here on slide number 5. There's a graph, and we see that there's one line that has like the little dots, and it's all connected, and then there's another line that's kind of straight, and then it starts to curve as we move across the x-axis on the wavelength. The line that has the dashed edges to it at the very top, that's the classical theory line. The line that's connected with the tiny little dots to it, that's the modern physicist line. This is what Planck thought, okay? Classical theorists thought as wavelength gets smaller, intensity gets higher. No one really did experimentation on this. This is just what we thought. This is the reason why we see these dashed lines here, because they're extrapolating. They're pretending like it's really there when it's really not happening at all, okay? So classical theory is saying, as wavelength gets smaller, intensity is going to get higher. But that's really not what we observe in nature. That is not what scientists really see. What they actually see is where we see these little dots. So we're actually going to look at it. I want you to look at this graph in an opposite way. And actually, let me just draw this on the board. Okay, give me a second. Okay, guys. Okay, here's my graph. Okay, so the black represents Planck's theory, which just means it's the modern theory. So this is what we know today. The blue represents what classical theorists thought. So this blue here, this is intensity. This lambda represents wavelength. So let's look at this. The reason that I'm saying that we want to look at this backwards is because typically we would read it from this way. Sorry, guys. Okay, typically we would read this graph from this way to this way, but I actually want you to look at it a different way, because as we go across here, wavelength gets larger, but I want to look at it as wavelength gets smaller.